A very good evening, my dear students. We are in Unit 5, which is about RF system design concepts. From Units 1 to 4, we studied about transmission lines and waveguides, and that was up to megahertz range. Now, coming to RF system design, we are going to hereafter see or deal with frequencies in the gigahertz ranges. So these are the topics we're mainly going to cover in this particular PowerPoint presentation. The first one is about what is radio frequency. Then we'll see about what is the frequency that will be covered, which is about the spectrum, like what is the range of frequency that will be covered in the RF and microwave. We will see what is power, what are RF networks, and a special type of parameters called as the S parameters. So let us start seeing one by one. We would have heard about the term RF. It stands for radio frequency. So this radio frequency is mainly between a range of 1 to 3 gigahertz. So most of the wireless communication, it follows that particular frequency between 1 to 3 gigahertz. It comes under the radio frequency range. Any frequency between 3 to 30 gigahertz, it comes under our microwave frequencies, and above 30 up to 300 gigahertz, they come under a special range which is called as the millimeter wave frequencies. Millimeter waves are the current topic of research. They are actually called as the terahertz frequency ranges. They are used mostly in medical applications for scanning systems. Like we have MRI scans, PET scans for cancer diagnosis. So the frequency that they use to point out to cells in cancer diagnosis is in this particular millimeter wave ranges because they are not harmful to our human body. The next one is about frequency and wavelength. I guess we are very familiar with the definition for frequency. So what do you mean by frequency? In a time duration of 1 second, how many cycles are present? That is what we call to be the term frequency. So here there is one full cycle in a duration of 1 second, which means the frequency of this is 1 hertz. So to define what is frequency, the number of electromagnetic wave cycles that pass per unit time. So the number of cycles present in a duration of 1 second is what we define to be frequency. Then we are talking about gigahertz ranges here. So for RF ranges, then within the same 1 second, I need to have, giga means it is 10 power 9. So I need to have 10 to the power of 9 cycles within a period of 1 second. That is why we say the waves travel very, very fast. Coming to the next definition is about wavelength. So wavelength we usually define as the distance between either the two maximas or the two minimas. This definition holds quite good. Or in other terms, we can also say as the distance after which the fields repeat. So this wave, it is going to start repeating here. So from here, this distance to this distance, this is one cycle, this is next cycle. So this distance is what we term to be the wavelength of my particular wave. So frequency means the number of cycles in a duration of 1 second or per unit time we call it to be frequency, and wavelength we usually call it to be the distance between two maximas or the two minimas or the distance after which every wave repeats. That can also be termed as the wavelength. Now we will see about the spectrum of the RF and microwave ranges. So this diagram tells the entire electromagnetic spectrum. Out of this particular region, what the arrow mark shows, till 10 power 9 gigahertz, this is our area of interest right now. This covers both the RF region, the radio spectrum, as well as the microwave spectrum. So most of the wireless communication, the microwave events, our modems, all falls under this RF and microwave ranges. Whereas, as I said, the terahertz range, which is the millimeter wave, so this, as this diagram shows, it is mostly used in medical imaging systems where MRI scans, PET scans, etc., where such high frequencies are passed through human body to detect any medical issues. So, but we're not going to say about this much now because it is under research. We are mainly going to concentrate up to this microwave range. Now we'll come to a term called as power. What do you usually mean by power? If I say that I can run at a very high speed, I'll say that I have more power. If someone runs a little bit slower than me, we will say that he has less power. So the term power can say different things. It can say how much distance a wave can travel. It can say how much energy can be delivered. And it can also say how pure or without distortion whether my particular signal has reached my receiver side. So if my signal has reached without distortion, if I've conveyed full energy, if I've traveled much distance, we can say that my signal is a very, very powerful one. Yes. So after this, we need to concentrate more because the terms we are going to encounter after this, they are a little bit new to us. We are going to get introduced to RF networks. So what are usually networks? For example, I'll draw something. Let this be some device I'm testing. So this is what I call to be my network. Here I can give some input. This is going to give me some output. So this is my device under test. Here I give my input, and at this side I'm going to get my particular output. So this is my network which I'm going to test, and this input and the output, these are called as ports on a network. So any device that contain input port and output port, or any device that contain ports, we call them to be networks. So to define what is a network, a device that has one or more ports, they can call to be networks. So this is an amplifier actually. You can see it here. This is an example of an amplifier. It has two ports at the input side and two ports at the output side. So this is an example of a two-port network. This is an example of an antenna we have seen at our rooftops of the home. So antenna is an example of one port network because it gets signal from one side and it transmits wirelessly to the receiver at the other side. So this is an example that comes under one port network. This is an example of two-port network which we saw already. And this is a directional coupler. So this is an example of directional coupler. We have studied about directional coupler in unit 2, I think, in the measurement of VSWR. So if you see the directional coupler contains, this is the first port, this is the second port, and this is the third port. This is the whole we said that will be present in the directional coupler. So this is an example of a three-port device. So any device that contains ports which can receive energy and pass energy, we call them to be networks. So a port can pass energy, absorb energy, as well as reflect energy. Right. Now let us start to analyze networks. So we saw in our previous slide, these are called to be networks. There are some devices, they contain input terminals and output terminals. Now how I'm going to perform measurement at these particular networks? That is going to be our next slide. How I'm going to analyze any given network for us. So as we said earlier, this is my network which I'm going to test. This is my input port. So here there are three ports actually. Let us assume port 1 as the input port, and port 2 and port 3 I'm receiving some output signals. Analyzing networks means how measurements are going to be made at a particular network. Fine. So I'm giving the input here. I'm going to take the output at port 2. How I'm going to measure this particular network, that is what we mean by analyzing networks. So if you see about voltage and current and high frequency signals, we saw in the general solutions of transmission lines, the voltage was not a single quantity. It contained a combination of two voltages. One we call to be the incident voltage and the second we call to be the reflected voltage. Right? So when I talk of high frequency hereafter, the voltage and current are no more. They are no more single terms. They are a combination of two or more terms together. We call voltages as incident voltage, reflected voltage. We can say the current might get transmitted, current might get absorbed in the network, and so on. But when we studied circuit analysis in our second semester, we saw current as one quantity, voltage as a single quantity. We never bothered about whether the current was incident, reflected, and so on. So hereafter, when I analyze high frequency networks, the current and voltage are not just single terms, they are a combination of two or three terms combined together. Voltage means it is a combination of incident and reflected voltage. Similarly, current means the current might be transmitted or it might be absorbed by a particular network. So we are going to make measurement based on whether the waves are reflected or whether we are going to measure the waves at the corresponding output ports. Yes. So this is a very important parameter as far as high frequency networks are concerned. When we studied about low frequency circuits, I think we would have studied what are Z parameters, Y parameters, we know what are hybrid parameters, and we would have studied what are ABCD parameters, right? My ABCD is horrible, kindly forgive me for that. Yes. We have studied about the ABCD parameters. But all these Z, Y, H, ABCD, they measure voltage and current as only one single term. We either measure the voltage and current at the input side as one quantity, or we measure them as a single quantity at the output side. But hereafter in high frequency, as I said in the previous slides, the voltages and currents are no single quantities. The voltage might get reflected, the voltage might pass through. So it is going to be a combination of various terms together. So for such kind of analysis, I cannot use this Z, Y, H and ABCD. I need to use a special type of parameters called as S parameters. So S parameters are how we are going to make RF measurements, and S stands for scattering. They tell me whether the wave is going to be a reflected wave or I'm going to measure the wave which is obtained from the other output ports. Are you clear? I'll just repeat once again. When we seen low frequency circuits, we used Z, Y, H and ABCD parameters. We used to open circuit, we used to short circuit and measure the various voltage and current values. But when I come to RF and microwave ranges, which are in gigahertz ranges, I no longer can perform open circuiting and short circuiting. That is no more possible. Also, the voltage and current are not singular terms hereafter. It is a combination of various quantities of voltage and various quantities of current. So we cannot use the same Z, Y, H and ABCD we used in low frequency circuits here also. I need to define a new set of parameters which are capable of measuring at higher ranges, at RF ranges, and those kind of parameters are what we call to be the S parameters, where S stands for scattering. And S parameters are represented as Sij, where I represents where I'm getting the output, J represents where the particular input is given. So in this particular diagram we can say that this is my I, this is my J. I get the output at port 2, I give the input at port 1. So the parameters represented as S21, where 2 represents the output port and 1 represents the particular input port. Yes. This particular line I made it to appear at the last because this is again not a single measurement of voltage or current. My waves are traveling in nature, so the waves might get attenuated, the voltage might vary, the current might vary, and due to all these factors we can no longer use the same ZYHABCD. We come to our new set of parameters called as S parameters. Right. Now let us take an sample two-port network and we will see how the measurement is being made. So this is a two-port network. So two-port network means This is my device. I'm having two ports this side and two ports this side. I'm going to define new parameters called as A and B, both at the output side and the input side. So I'll write AB here and AB here. So this is my port 1. This is my first set of ports. This is my second set of ports. So I'll name this as A1, B1, A2 and B2. Usually in two-port network analysis, A represents the incident wave, which is towards your network. So I'll be having it like this. A represents the incident wave and B represents the waves reflected from the particular two ports. So A1 and A2 represents the incident wave at this particular network, and B1 and B2 represents the reflected wave at the two networks. Right. Now for any two-port networks, four kinds of S parameters will be present. They are called as S11, S21, S12 and S22. We will see one by one. I'll start with the first term S11. So what does this 11 represent? 1 represents the output port. This represents the input port. It is usually denoted as Sij, where I represents the particular output port and J represents the particular input port. So come to this S11. So 11 means the output port is also port 1, input port is also port 1, which means the wave is reflected at port 1 itself. I give input at A1, it is reflected as B1. So that parameter is called as S11. Now come to S22. It is again input is given at port 2. The wave is reflected at the same port once again. So it is S22. A2 is your incident wave. B2 is a wave reflected at port 2 itself. So we call this to be the parameter S22. Next we'll see what is S21. So S21 in the sense I give input at port 1. I get the output at port 2. So this is as S21. And about S12, I give the input at port 2. I get the output at port 1. So this is called as S12. So to be clear, J represents your input port and I represents the particular output port. So S12 means port 2 I am giving a particular input, and at port 1 I am measuring what is your required output. Right? So as we said, we have four S parameters: S11, S21, S12 and S22. The general definition for S parameters are, they are the ratio of the voltage that we measure or whatever we measure at the output to the corresponding input terminal. So S11 means it is B1 by A1. S21 means B2 by A1. S12 means B1 by A2. And S22 means B2 by A1. So this is your particular output port. This is your particular input port. So in general, S can be written as, it is B divided by A term. Fine? Yes. So these are the important properties of S parameters we need to see. S parameters possess a lot of important properties. I'll just tell you one property among all the available properties. So the S parameters are usually represented by matrices. If I take a two-port network, I represent it as a 2 cross 2 matrix, because for a two-port network, 4 S parameters are there: S11, S12, S21 and S22. So for 4 parameters, we represent it as a 2 cross 2 matrix for a two-port network. So in general, for n ports, we will be having a n cross n matrix. So the general representation of the S parameters are B is equal to S into A, where B represents the wave that is reflected, S represents the S parameters, and A represents our incident wave. And for two-port network, we have 4 S parameters: S11, S12, S21 and S22. So one port means only one S parameter, Two port means it is 2 cross 2. So 4 S parameters. 3 port means it is 3 cross 3. So it is 9 S parameters in total. So now writing in this form of matrix, for a two-port network we have 2 incident waves and 2 reflected waves. So the 2 incident waves are B1 and B2. This S represents the 4 S parameters S11, S12, S21, S22, and A represents the 2 incident waves A1 and A2. So in matrix we write it as A1 and A2. So the general matrix representation of S parameters for a two-port network are B1, B2 is equal to S11, S12, S21, S22 into A1, A2. So in the form of equation we can write it as B1 is equal to S11 into A1 plus S12 into A2, and B2 is equal to S21 into A1 plus S22 into A2, which gives rise to these two equations. So this term is very important for us. Why S11, S22 are called as reflection coefficients and S21 and S12 are called as the transmission coefficients. Now what is S11 and S22? Let me just go back to the previous slide. Yes. So what is S11? I give the input at port 1. It is reflected at the same port. So this terms a reflection coefficient. Once again, at the output port, I give A2. The wave is reflected at the same port, which is B2 itself. So S22 is again a reflection part. So therefore S11 and S22 contribute to reflection terms. What about S21 and S12? S21 means input is given at A1. It goes through the network, we measure at B2. Here input is given at A2. It goes through the network, we measure at B1. So these two are called to be the transmission coefficients. Thus, S11 and S22, we call these two terms to be the reflection coefficients. S12 and S21 are called to be the transmission coefficients. So just have a quick summary what all we saw in this particular presentation. We saw what is a network. So it is any device that contains a port we call to be a network. And the purpose of port is it passes energy, it absorbs energy, and it reflects energy. And S parameters are used when we come to very high frequency networks because we can no longer use the same Z, Y, H and ABCD parameters. So therefore, to measure RF networks, we are not going to use Z, Y, H and ABCD. We are going to use special kind of parameters which are called as the S parameters. So hope you're clear with what we saw in this PowerPoint presentation. So these are the basics of the upcoming derivations of Unit 5 fully. Only if we understand what are S parameters, we can solve the characteristics of RF networks. We have to design RF networks. So to design any RF networks, we need to know what S parameters are. So have your mind clear on what S parameters are and why Z, Y, H and ABCD cannot be used for RF frequencies. Thank you very much.